Dear student, today I am going to discuss the next part of strength of organic acids and bases. So in this video, some key features we have to remember that if the aromatic ring is substituted with electron withdrawing group, then it shows either minus I or minus R effect. That is electron withdrawing inductive effect or electron withdrawing resonance effect. But the electron withdrawing resonance effect is always more powerful as compared to electron withdrawing inductive effect. So, electron withdrawing resonance effect stabilize the conjugate base more effectively as compared to electron withdrawing inductive effect. So, stability of conjugate base increases, the rate of dissociation also increases. Because of that, acidity of compound also increases. But when this happens only if the group is present at ortho and para position, then only it shows more effect as compared to meta. So always remember students, it's no doubt you may have an electron donating group or electron withdrawing group. If they are situated at ortho and para position, then only it affects on the acidity of compound. If it present at meta position, then its effect is less, but major role if that group is present at ortho and para position. Let us look at the next example. Now this is a phenol, and in the next compound, the presence of nitro group is there at ortho position. In the next, there is a presence of again a nitro group at para position, and then the presence of nitro group at meta position. So now what is the first of all we have to see what is the role of nitro group. As we discussed already in previous slide, nitro group shows electron withdrawing effect. Why it shows electron withdrawing effect? Because this nitrogen carry a positive charge. So because of this nitrogen carry a positive charge, it withdraw the electron density from the electron rich aromatic ring. That's why this one is nitrogen is electron deficient. Therefore, it withdraw the electron density from the electron rich aromatic ring. Hence, nitro group is electron withdrawing group. So, in phenol, there is absence of electron withdrawing group. That is, NO2 group is absent. Therefore, minus I or minus R effect is absent. That is shown by NO2 group. But which group is present? But there is a presence of minus R effect. That effect shown by pH group. That is, this phenyl group also shows electron withdrawing resonance effect. So this effect is present. This resonance is less powerful as compared to remaining structure as carbon share the negative charge. So if you show the resonating structure for this, once you get a phenoxide and after this resonating structure, the carbon carry the negative charge here. But if after the dissociation of H plus ion in orthonitrophenol, paranitrophenol, then the negative charge after delocalization, it will be on oxygen. So because of this, oxygen carry a negative charge very well as compared to the carbon. So because of this, the resonance effect, that is the electron withdrawing resonance effect in compound B and compound C is more powerful as compared to compound A. But in case of meta compound, so in case of meta compound, only which effect is possible? Only the minus I effect is there, because NO2 group, if it is situated at meta position, then it never show resonance effect. That is, the NO2 group not going to take part in a resonance. So because of that, now in meta compound, that nitro group shows only minus I effect. So as we already discussed, minus I effect is less powerful as compared to minus R effect. Hence, here that conjugate base is less stable as compared to ortho and as compared to para. but it is more stable as compared to phenol. The reason here, one more effect is there, that is a nitro group shows a minus R effect, minus I effect, while in case of phenol, minus I effect is absent. So in case of this in case of ortho, what are the different effects present? That aromatic ring shows this aromatic ring shows electron withdrawing resonance effect, and this NO2 group also show electron withdrawing resonance effect. So at the same time, this in case of para, again the nitro group shows electron withdrawing resonance effect, but in case of meta, the nitro group shows electron withdrawing inductive effect. Let us we discuss one by one. Now this is the orthonitrophenol. Orthonitrophenol, as it is an acid, so after the dissociation of this, that is once the proton is going to release, it gives this conjugate base is generated and H plus ion. Now look at this conjugate base, how the conjugate base is stabilized by way of a resonance. So during this resonance, the nitro group takes part in the resonance. So because of this resonance, now look at here that oxygen carry the negative sign. So this resonance is more powerful. Now what are the different here? The minus R effect and minus I effect is present, shown by NO2 group. So because of this, this conjugate base is highly stable. If we look at the second molecule, that is the meta group, if it is present at meta group, after dissociation, whatever the conjugate base result, and if you are going to show the delocalization of negative charge, what you see that NO2 group not going to take part in a resonance, that this carbon carry the negative charge. So here NO2 group not involved in resonance, only minus I effect is present. But in case of para, now look at that NO2 group takes part in the resonance. So because of that, this resonance effect is more powerful, because can you see this structure is more symmetric structure. So if the symmetric structure is there, then always that structure is having more stability. So this structure having more stability, and again one more feature is here, that all the electron distribution is in the plane. If we compare it with the ortho conjugate base, in ortho conjugate base, you can see that the negative charge is delocalized, but that delocalization not symmetric, right? So we call this structure as a paraquinoid structure. And if you talk about in ortho compound, so in ortho compound, this structure is called as a orthoquinoid structure. So orthoquinoid structures are always less stable as compared to the paraquinoid structure. So this conjugate base is highly stable. If this conjugate base is highly stable, so what I had to say, the rate of dissociation is fast in case of paranitrophenol. Therefore, paranitrophenol is strong acid among all. If I compare this with phenol, so look at the phenol after dissociation, whatever the negative charge is generated on oxygen, that undergo delocalization, and every time the carbon share the negative charge. Because of that, this resonance effect is less powerful as compared to the ortho, meta, and para nitrophenol. So the order of acidity is para is strong acid as compared to ortho, and then meta, and then no substitution, that is a phenol. Now this is the next example, 2,4-dinitrophenol and 2,4,6-trinitrophenol. The name of this compound, common name of this compound is picric acid. Now look at the pK value. 2,4-dinitrophenol is 4.01 and the pK value for picric acid is 1.02. So from the pK value, what we conclude? From the pK value, we conclude that picric acid is a stronger acid as compared to the 2,4-dinitrophenol. The reason behind it, again, once you increase the electron withdrawing group, the number of electron withdrawing group increases, the acidity of compound also increases. So role of nitro group is electron withdrawing, role of nitro group is electron withdrawing. But when it is located at ortho and para position, then its effect is more. So as you are adding a new nitro group in case of a picric acid, again at ortho position, then its effect is more. So the conjugate base of picric acid is more stable as compared to 2,4-dinitrophenol. The more the number of canonical structure, the more effective is the resonance. So as one more nitro group involved in resonance, so automatically the more canonical structure. The canonical structures for picric acids are 6 and for 2,4-dinitrophenol are 5. So this is the 2,4-dinitrophenol. Now after dissociation, it gives this charge, this conjugate base and then conjugate base. So this is first, this nitro group take part in the delocalization, and after that, this nitro group takes part in the delocalization, and at the end, again, this going back to the oxygen and the structure is regenerating. Here, I am not showing the carbon carry the negative charge, so we can show that resonating structures also. So we can stop the resonance at here, we can stop the resonance at ortho position and at para position. So two ortho positions can carry negative charge, one para position carry a negative charge. So how many? Three positions, that is three positions where the carbon carry the negative charge, that is three canonical structure, and every time this nitro group take part in the delocalization, then this nitro, so total number, this is three resonating structure, this one is fourth and this one is 5. So how many total canonical structures are possible for 2,4-dinitrophenol? There are the 4 canonical structure, but here I am showing only the 4 canonical structure. Now this is the example, this is the trinitrophenol, that is the picric acid. So after dissociation of acid, so this conjugate base, now here the resonating structures are shown again in the same way in previous structure, that is I am not showing a carbon carrier negative charge, but that resonance structure is also possible, but you can see that in previous example, there are 4 canonical structure. As you increase one number of nitro group, so automatically the canonical structure increases to 5. So first canonical structure, when the nitro group which is present at ortho position involved in resonance, then para nitro group which involved in resonance, then meta nitro group which involved in resonance, and at the end this go back to oxygen. So there are 5 canonical structures. Number of canonical structure increases, the effect of the resonance is more powerful. Therefore, the picric acid is strong acid as compared to 2,4-dinitrophenol. Now, the next, what we had to look at in this example now, in previous example, what we discussed that if the electron withdrawing group is substituted on the aromatic ring, now the next we can also have, if the aromatic ring is substituted with electron donating group, then it shows either plus I or plus R effect. As we already talked, that is electron donating resonance effect is more powerful as compared to electron donating inductive effect. So remember always, in the resonance effect is always powerful as compared to the inductive effect, because in resonance effect there is actual movement of electron from one atom to another atom, while in inductive effect there is a polarization of bond. So always the powerful effect is resonance effect. So plus R effect, what is the role of electron donating inductive effect? It destabilizes the conjugate base more effectively as compared to plus I effect. So because of the electron donating inductive effect or resonance effect, the localization of charge increases instead of the delocalization. Because of the localization of charge, the conjugate base is unstable. So stability of conjugate base decreases, the rate of dissociation also decreases, hence acidity of compound also decreases. The last factor is same as we discussed in previous slide, that is if the group is present at ortho and para position, then only it shows more effect as compared to meta. So the same we can see here, that is if the group, whether it is donating or withdrawing, if it is present at ortho and para position, then only we can see its more effect on the acidity of the compound. But if it is present on meta position, then its effect is little bit less. So this is the example. Now phenol, then orthocresol, metacresol and paracresol. So what is the role of CH3 group? As alkyl group is there, so role of CH3 group is electron donating group. So presence of CH3 group in compound BCD shows electron donating inductive effect. So it shows what? It shows electron donating inductive effect. While in case of phenol, as electron donating inductive effect is absent, therefore the phenoxide ion is more stable in case of A, that is conjugate base of A is more stable, hence the rate of dissociation of A is fast, and from the pK value you can see this is 9.95 as compared to the remaining. So smaller the pK value, stronger is the acid. The reason behind it, the phenol, there is absence of plus I effect. Because of the absence of plus I effect, this phenoxide ion is more stable, hence the rate of dissociation is fast and hence it is a strong acid. But when we compare between the among the B, C, D, so among the BCD, as we already talked, if the group is present at ortho and para position, then it affects a lot. So look at the B, compound B and compound D, they are weaker acid as compared to C. So if the electron donating group is present at meta position, then its effect is less. So C is strong acid next to A. So A is a strong acid, next to that C is a strong acid. But if we compare between the B and D, what you can see that methyl group is present at ortho position, while in case of para, it is at para position. As inductive effect depends on distance, so as this CH3 group and this hydroxy group, they are away from each other. So here electron donating inductive effect is less. If the plus I effect is less here, so plus I effect less, therefore automatically increase the stability of conjugate base. If it increase the stability of conjugate base, that means the rate of dissociation of D is fast as compared to B, right? So D is a strong acid as compared to B. So the final order of acidity is A is strong acid, the reason absence of electron donating group, while C, next to that C is a strong acid, the reason though there is a presence of electron donating group, but it is present, this group is present in meta position, and when the group is present in meta position, its effect is less. So that's why C is the next next more acidic compound. In case of B and D, the inductive effect depends on distance. So in case of D, electron donating inductive effect is less. Therefore, conjugate base of D is more stable as compared to B. So because of that, D is more acidic as compared to B. So for this, students, you go through the reference book that I have already mentioned over here.